In the last video, we ended on proving the Pythagorean theorem for two vectors x and y in Rn where x and y are orthogonal. So here is the Pythagorean theorem, and here's the work we did in the last video. You can look back at it in the last video if you want to remember what we did. But what I wanted to say about the Pythagorean theorem is we know that this is true. We've seen it for right triangles. So if we have a right triangle with sides A, B, and C, we know that a squared plus b squared is c squared. And what we've done is we've proven this because if we let's say A be this vector here, starting, let's say this is the origin, and then B is this vector, then you would get this vector C right here. Because B plus A, which is the same thing as A plus B, that is going to be this vector C. And so from what we have here, we have that C squared, which is this x plus y, the length of that squared is a squared plus b squared. The next topic I want to talk about is scalar and vector projection. So suppose we have two vectors, x and y. Let's say this one's x and this one's y. And y doesn't have to be longer than x, it could be shorter. We want to project x onto y. Now I'm going to go through all the details of this. You don't have to memorize the details. You just need to know the formulas. You don't really have to memorize the formulas either, but you do need to be able to work with them. I'm sure you've seen this before in Calc 3, but yeah, I'm going to go back through it just in case you forgot. So if we have the vector x and the vector y, and let's say we have an angle between them, let's call this theta, then when we project x onto y, what we're doing is it's like we have this sun, let's make it a red sun, it's above x, let's give it two eyes and a mouth, and it's smiling, and it's going to make a shadow, and this shadow is going to be cast onto y. Y is the horizon here, like the horizontal line, and so we're making this shadow, and this vector that's made, that's in the direction of y, but stops at the end of the shadow, we call that P. And P is the projection of x onto y. So what we want to do is we want to try to figure out a formula for P. How we're going to do that is first we're going to note that for y we have something called a unit vector. Let's put it right here, u, and this unit vector is y divided by its length. Okay, we're going to use that because that tells us the direction we want to go, and P is going to be some scalar times this directional vector, this directional unit vector. Okay, so we need to figure out what P is. How do we do that? Well, first thing we're going to do is we're going to look at this vector here. We're going to call this vector z. What is z in terms of x and p? Well, z, it starts at p and ends at x. How can we write that? Well, it's like going up x, and then if we go backwards p, let's say this is negative p, what do we get? We get a vector right here, which is parallel and has the same length as z. And remember that vectors, you can move them in any direction, and it's still the same vector, as long as it has the same length in the same direction. So this vector is z. So z is the same thing as going along x, and then going backwards p. Okay, so I'm going to erase all of this because I don't need it. So let's write that here. Z is equal to x minus p, but at the same time, x is equal to z plus p. If I just solve for x here. There's a reason I'm doing this. I'm going to take the dot product of p and x. And let's see where that takes me. So if I take the dot product of p and x, well, this is p and z plus p. Okay, which is, this is actually linear. This is a linear transformation here. But we can write it out. This is p transpose z plus p, which is p transpose z plus p transpose p. So what I'm saying is this is the same thing as the inner product of p and z, the inner product of p and p. So this is p and x. But this vector p, because it's in the same direction as y, is going to be orthogonal to z. So p is perpendicular to z, which tells us that the inner product is 0. So we can cancel this out and we get 0. So what we're left with is this dot product is equal to the dot product of p and p. But p is a scalar times the unit vector. So we get alpha times u with x is equal to alpha u. And we can take this alpha out. This is going to come out as alpha squared because I have 2 of them. You can double check it doing something similar to what I've done here. The dot product of u with u. Or you could even do this if you want to. This is, well, let's leave it like that. Alpha squared, the dot product of u and u. But what is the dot product of u and u? So that's the length of u times the length of u times cosine of the angle between them. The angle between u and itself is 0, so this just becomes 1 because cosine of the angle 0 is 1. And the length of u, by definition, is a unit vector, so these are all 1. So we get alpha squared. And now let's work on this side. I can take this alpha out. And then here, I'm going to do the same thing as what I did over here. This is the length of u times the length of x times cosine of the angle between them. And we actually labeled that angle as theta here. The angle between x and y is the same thing as the angle between x and p, or x and u. And then I have this alpha here, and by assumption it's not 0. So I get, oh, and this is has length 1. So I'm left with alpha, the length of x, cosine theta, and I can get rid of one of these alphas. So I get alpha is the length of x times cosine of the angle between them, and that is our scalar projection, the scalar we would get to put in front of u. So p is alpha times u, which is the length of x times cosine of the angle between x and y times u. But what can we do with this? If you know what this is, then you can figure out p just fine. But most of the times we're not given the angle between 2 vectors. So I want to come up with a formula for p that doesn't involve the angle. So what I'm going to do is I know that theta is the angle between x and y. And we know that cosine is, this is just the formula for the dot product solved for cosine of theta. So I'm going to insert this here. So I get the length of x. I'm going to circle this so you know what I'm doing. I'm going to put this in. So I get the dot product of x and y over the length of x times the length of y times u. And I'm actually going to put make a substitution here too, because this length, we know that u is equal to the length of is equal to y divided by its length. And so let's put that in as well. So put it right here, y over the length of y. And now we just kind of clean this up. We have this crosses out, two of these, and we're left with this number, the dot product of x and y, all divided by the length of y squared, because I've got two of them, times this vector y. And what does that leave me with? This is probably the formula you're most familiar with. This is x transpose y. This thing, remember that the length of y is the square root of y. But if we square it, we get rid of the square root. So we have y transpose y times y. And that is our vector p. So these are the two formulas you want to know. If you're given the angle between the vectors x and y, and you know what the length of x is, you can find alpha this way, and then you can just multiply it by the unit vector. But if you're not given the angle between them, but you do know the vectors themselves, this is how you can find the projection of x onto y. Let's do one example, just so we've seen it and we know how to do it. Yeah, here it is. Let's find the vector projection P of x onto y, and then we want to verify that P and x minus P are orthogonal. Here I'm giving you two vectors in R3. X is 2, 4, 3, and y is 1, 1, 1. And I don't tell you what the angle between them, the two vectors, is. So we're going to use, for the vector projection, this x transpose y, y transpose y times y. Okay, let's figure out what this is. So x transpose y means I take the dot product of these two. This is, I'm going to switch to a different color. So 2 times 1 plus 4 times 1 plus 3 times 1 divided by, now take the dot product of y with itself. It's 1 squared plus 1 squared plus 1 squared, and multiply it by the vector y, 1, 1, 1. Okay, what am I left with? This is 2 plus 4 plus 3 over 3, 1, 1, 1. Looks like I get 9 over 3, 1, 1, 1, which is just the vector 3, 3, 3. Or you can write it like this. If you don't want to take up so much space, you can just write it as the transpose. So you see this vector, you can see that this lies on this vector. It's actually longer. The length of this vector is longer than this one, right? It's 3 times the length of this one. But you can see that it is a scalar multiple of y. And so that makes sense. We have this vector x, and this vector y. And when we projected it, we got a vector that was in the same direction, but just a little bit longer than y.